In this video, we're going to look at how scientists discovered that atoms have a nucleus in them. This discovery was made by Ernest Rutherford, as well as his colleagues, in 1911. And they made this discovery with their famous gold foil experiment. And we're going to talk about that here. So atoms. This is sort of how we think about atoms today, with electrons on the outside, and then in the middle, a dense, hard nucleus that's where the protons and neutrons live. But it wasn't always like this. Before Ernest Rutherford and his co-workers did their experiment, this is what scientists thought the atom looked like. They called it the plum pudding atom. Now, plum pudding is kind of a British thing. So if you're American, it might be better to call this the blueberry muffin model. Think about this. You take a blueberry muffin and break it in half. What do you see on the inside of that muffin? Well, you'll see blueberries, and the blueberries are just kind of randomly stuck into dough. And that is exactly what scientists thought the atom looked like at a very small scale. That electrons were sort of like blueberries, and they were stuck in this dough, kind of, that was positively charged. So you got this positively charged dough with electrons stuck randomly in it. This is the plum pudding model, but of course it turned out not to be true. Here's how Rutherford and his co-workers showed that the atom had a nucleus and that the plum pudding model wasn't right. They started out with a piece of gold foil, which is like tin foil or aluminum foil, except it's made of gold. I mean, wouldn't this be awesome to like wrap your sandwiches in for lunch? Anyway, I don't know, maybe if you're really rich, you use gold foil to like prepare your lunch. Anyway, they took this piece of gold foil and they shot tiny little things at it. What they shot at it were called alpha particles, which are tiny positively charged particles that are much, much, much smaller than an atom. So they take the gold foil, they bam, 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 shoot alpha particles at it. Now they want to know what happens to the alpha particles after they hit the gold foil. So here's what they do. They take a material that flashes when it gets hit by alpha particles, and they take this material and they bend it around into a circle like this. So wherever the alpha particles hit, they'll see a flash. They take this material, and then they take their piece of gold foil, and they put it right here in the middle of this circle. So now they shoot alpha particles into the gold foil, and they'll see a flash somewhere on this circle that will tell them where the alpha particle ended up after it hit the gold foil. Now here's what they see. Most of the time, they shoot alpha particles, bam, 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 here at the gold foil, straight on, and they see flashes right here, behind the gold foil. So this would indicate that the alpha particles are going right through the atoms of the gold foil and are ending up over here. So that's the first thing they notice. The second thing is a really huge surprise. When they shoot the alpha particles every once in a while, they don't see a flash here. Instead, they see a flash over here, or a flash over here, or sometimes a flash here or here, which makes them think that the alpha particles are hitting the gold foil and are veering off to the side once in a while. Or sometimes they're hitting the gold foil and they're bouncing back completely all the way back. So we can kind of summarize what they see using a diagram like this. Here we've got our circular detector screen that flashes. Here's an alpha particle emitter, which is just a fancy word for an alpha particle gun, something that's shooting alpha particles. Most of the time these alpha particles hit the gold foil and they go right through, and we see flashes on the screen on the other side. But every once in a while, an alpha particle will hit the gold foil, zoom, zoom, and will veer off to the side and flash over here. And every once in a while, it will hit the gold foil and will bounce back almost 180 degrees. Flash here and flash here. So, based on these two pieces of information, Rutherford and his team are able to make some conclusions about what the atom actually looks like. Here's the conclusions that they come to. Let's start with this gold foil, okay? The gold foil that they use is incredibly, incredibly thin. And in fact, it's so thin that these guys reason that there are only a few atoms in its thickness, that it's only a few atoms thick. So let's look at it on its side here and look at a magnified view of the gold foil. If we want to think about gold atoms as being sort of circles or balls, this is what the view from the side of the gold foil might look like. Just 2 atoms thick here. Now, let's think about the results that they got from the gold foil experiment, okay? The first thing that they saw is that most of the time, the alpha particles seem to have gone straight through the gold foil. So, based on this information, they're able to reason that most of the atom is empty space. Or if there's something there, it's very light. It's not very dense, and it's really easy for the alpha particles to shoot right through. So most of the atom is probably empty space. But now the second thing they see is that every once in a while, an alpha particle, zoom, veers off to the side, or it's like it hits the gold foil and bounces back. And so based on this information, they reason that while most of the atom is probably empty space, they think that there must be something very small but very hard inside each atom. And here's a drawing here. Of course, you know that this is the nucleus now, but they didn't know that the nucleus existed, so they had to discover it here. And so they think there must be something really, really hard. And when an alpha particle hits it head on, bam, that alpha particle's gonna ricochet back. And they also notice, as we said, that sometimes the alpha particle veers to the side. They say, well, maybe it's because it hits the nucleus on the side of it, so it goes off like that. Or they also said maybe since alpha particles are positively charged, maybe the nucleus is positively charged, so that if the alpha particle comes close to it, remember, things that have the same charge repel each other. So you've got this alpha particle coming close to a positively charged nucleus, then zoom, it's going to veer off to the side because they're pushing away from each other. So regardless, based on this information, they reason that there is something small and hard in the atoms that once in a while the alpha particles are banging into, and that's what's causing them to bounce back or to veer off course. And they also reason that whatever this nucleus is made of, it's probably positively charged because of the way it looks like the alpha particles are sometimes getting repelled and pushed away. So if you take these 2 pieces of information together, we can come up with a model for the atom that looks like this, where this is just a combination of those 2 things that I saw, where we've got these gold atoms lined up, and most of the time, if alpha particles pass through so they don't hit any nucleus here, they just go straight on through. But if an alpha particle hits this hard, dense nucleus, or is close enough to be repelled by its charge, it veers off or it bounces back. So here's how the gold foil experiment changes how scientists think about the atom. Okay, so as we said before, here's a plum pudding atom with these electrons stuck in a positively charged kind of pudding. But Rutherford's experiment shows that this isn't quite true. Instead, he comes up with a model like this, where there is a hard, dense nucleus in the middle, and that is where the positive charge is. So the positive charge isn't like this kind of blueberry muffin dough that's spread throughout the atom, but instead the positive charge, everything that I've drawn in red here, the positive charge is concentrated right here in the middle of the atom, and then there might be some electrons floating around on the outside, but they're certainly not held in place because of the positively charged dough. Now, this is just one piece in a puzzle of figuring out what the atom actually looks like. So shortly thereafter, Rutherford comes up with this model for the atom, but then scientists realize that the electrons probably aren't just stuck in place, and instead they think that the electrons are spinning around the outside of the atom, and you still have this hard, dense nucleus in the middle. And then only a short while after this, it's discovered that the nucleus isn't just a hard piece of positive charge, but that the nucleus is actually made of protons, each one of which has a positive charge, and then the electrons are spinning around the outside. Now this is what we call the nuclear atom, because it has a nucleus. So we've got the nucleus of protons, and then electrons spinning around the outside. But of course, you probably know this still isn't an accurate representation of exactly what the atom looks like. In fact, they're totally missing the neutrons. It wasn't until the 1930s that James Chadwick and his colleagues discovered that there are neutrons, neutrally charged subatomic particles, in the nucleus of an atom. And then, as I've alluded to before, it's not that the electrons are really spinning around in circular orbits, but it's more like they're just buzzing around like crazy hyperactive flies all over the atom. But we'll get to all that later. For right now, all you need to know is that Ernest Rutherford's gold foil experiment showed that the atom was mostly empty space, but that it had something hard, something dense, and something positively charged that the alpha particles sometimes hit and bounced back. Now I want to talk about one more thing that can be confusing, but it's really important. And it has to do with the predictions that Rutherford made, what he was expecting to see. Okay, now when people first learn about the gold foil experiment, they're often really shocked that the alpha particles went straight through the gold foil. And they think that Rutherford and his coworkers must have been really shocked as well when they found this out. But it turns out that Rutherford was actually expecting the alpha particles to go through the gold foil. He thought that if atoms were the plum pudding model, that the alpha particles would have gone straight through. Because he thought that this positively charged dough was so light that the alpha particles would just be able to pierce right through it like bullets through a giant blueberry muffin. And sure, there are some electrons there, but compared to an alpha particle, an electron is so tiny, it's like a poppy seed compared to a bullet. And so he thought that that bullet would just fly right through the plum pudding atoms. Now, if you want to think of a model of the atom that would have made the alpha particles bounce away, it would have been Dalton's model, which was one of the first models of the atom. Dalton thought that atoms were hard, indestructible balls. And so if atoms had really been like Dalton thought, sure, the alpha particles would have hit them and would have bounced away. But if the atoms were the plum pudding model, because this positively charged dough is so light, Rutherford thought that the alpha particles would go straight through. So when it turned out that the alpha particles went straight through the gold foil, it wasn't really that much of a shock. But what was a shock was when sometimes the alpha particles would veer off to the side or would bounce back. This is what was really shocking. And it told Rutherford that instead of the positive charge being distributed throughout in this kind of dough, that the positive charge was concentrated here in the nucleus. So that's what led them to the model of the nuclear atom with a nucleus. So it might even be better to draw the nuclear atom like this, where instead of having this pink positively charged dough, there really isn't anything here at all. And it's just all of this positive charge is focused right here in the middle of the atom. Now, it's almost not even good to draw these atoms as if they're shells with a nucleus in the middle, because it's not like they have shells. A more accurate way to talk about this is to say that the shells, what I'm drawing as the shells, are really just the outer limits of where the electrons go. Okay? And so what's between what I'm drawing as a shell and the nucleus is really just where the electrons live. But they're tiny and they're moving around all the time, so there's really not much there. So in fact, maybe one of the best ways to draw the nuclear atom would to be like this, where there isn't a shell, but there's a nucleus in the middle of each atom, and then you can kind of see a circle here, which is the outer reaches of where the electrons go. But then, of course, this isn't a perfect view of electrons, because instead of going around in circles, they sort of buzz around in various shapes. But again, that's getting a little ahead of ourselves. What the main important points are here is that Rutherford's gold foil experiment disproved the plum pudding model of the atom. It wasn't that there was positive charge all throughout the atom, like the dough in a blueberry muffin, but that it was the positive charge was heavily concentrated in a very hard, very dense nucleus in the middle of the atom, and then the electrons were on the outside of it. So that is how Ernest Rutherford, Hans Geiger, and Ernest Marsden discovered the nucleus with their gold foil experiment.